Our next talk is entitled Spatial Eigenanalysis of 2D Deformation Energies. And the authors are Huamiao Wu, Kui Wu, and Theodore Kim. But they are either, the first author is from Yale University, and the two last authors are from Lightspeed in the USA. But the presenter is Alvin Shi, because there was a visa issue. Therefore, Alvin will give the talk.
This? Hello, everyone.
Please, Alvin.
Yeah. Okay. So, as our lovely introduction stated, I'm Alvin. I'm here in place of Huamiao Wu to present her work on spatial eigenanalysis of 2D deformation energies. So let's get started. 2D elasticity can be seen in many different applications, such as in dynamic simulation. Oh yeah, sure. Sure. Or surface parameterization, where 2D deformation energies get minimized. Is this good? Okay. Is this good? Okay. Yeah. Or surface parameterization, where 2D deformation energies get minimized. For triangle meshes using finite element methods, the main thing governing elastic behaviors are elastic energies, psi over here, which are functions of x, the spatial position vector describing the shape state, usually just a stack of vertex positions. For a small example, take static problems. The internal and external forces should balance out, subject to constraints, and because elastic forces are usually non-linearly dependent on vertex position, we must use Newton's method to linearize the equation and sort of take time steps, as seen in this linear equation here. H of x is the energy Hessian, which of course is the second derivative of our elastic energies with respect to the vertex positions x. Now, for a small, simple triangular mesh, we can imagine that as the number of elements increases, H becomes a large sparse matrix. This large sparse matrix is often not semi-positive definite, which makes it challenging to converge when using preconditioned conjugate gradient solvers, or PCG. So, we need an SPD projection for stably solving the system. And because directly projecting the whole global H matrix is usually not feasible, previous works have found ways to sort of simplify this whole projection problem. First, instead of looking at the large global Hessian, people start by examining local Hessians per element. In this case, for our use case, it'll be per triangle. Eventually, they get distributed back into the global degrees of freedom and get summed up to generate the full global Hessian as seen here. And because a sum of semi-positive definite Hessians must also be semi-positive definite, a convenient method for doing such projection is to just project each element before inserting it back into the global Hessian. For each of these individual Hessians, especially in deformation, the position-based Hessian can be written in terms of the deformation gradient, which we will denote here as F, and some extra things thanks to our use of the chain rule. Previous works have only studied that highlighted term in the red box, which, when you do semi-positive definite projection, does result in a semi-positive definite Hessian in terms of the positions as well. Such examples can be seen for volumetric simulation here, and also for surface tension energies as seen here. However, in order to get that final position-based Hessian, we need to multiply that middle term with partial f, partial x, heretofore called g, which is not orthonormal. This means that the spectrum of X-based and F-based Hessians are completely different. The X-based eigensystem must provide a more direct projection, but getting it analytically is not trivial. It's actually the content of the entire piece of work over here. So, we are going to be performing direct Hessian eigenanalysis for this position-based Hessian instead of just analyzing the F-based Hessian. To do so, first we recall a few so-called deformation invariants. Computing S, which is the symmetric part of the polar decomposition of the deformation gradient, we have I1, I2, and I3, which correspond to length, area, and volume preservation terms. Using these invariants, most elastic energies can actually be defined with these scalars, and the Hessian can be computed by using the chain rules in terms of them. For eigenanalysis, we will look at the final result H, including all of these terms, and not just doing semi-positive definite projection on each of these terms separately. We also note here that there's a lowercase f, that's just the vectorization of the deformation gradient, which is useful for avoiding having to use a lot of tedious tensor notation. Note that G is still partial f partial x, and in our 2D simulation cases, it is a 4x6 matrix. Notably, since it is 4x6, it has a two-dimensional null space, which means that already we sort of get two eigenmodes for free. The first one, of course, is a translation, and the second one is a similar orthogonal translation. Previous works have leveraged the property that all three invariant Hessians have eigensystems that align with each other. However, after applying G, the spectrums get mixed up. So, we can no longer analyze the Hessian of each invariant and then sum them up. We need to actually exploit properties of different particular energies to get the eigensystems that we are looking for. We start by looking at two pretty classical deformation energies. If we observe the expressions of these energies, we note that they are only dependent on 2 out of the 3 invariants per energy. Additionally, they are linearly dependent on I2 as well. So we split up our analysis into 2 different scenarios. One for energies that only depend on I1 and I2, which we call shape distortion energies, and one for distortion energies dependent on only I2 and I3, which we call volume preserving energies. We are going to start the derivation now. So, first off, in order to actually compute the G matrix, we do a little bit of definitions. Here, D sub m is computed from the rest vertex positions, x with the bar on top, and then we additionally define a 2x3 matrix D computed from D sub m, and also this useful matrix C, which helps with later analysis. The G matrix can be written as a Kronecker product of a 2x3 matrix, R 2x3 matrix D, and the identity matrix, which is useful since it actually reduces the dimension of the eigenproblem later on. Additionally, we will also be needing a few symbols representing the singular value decompositions of the deformation gradient and also D itself, which are denoted here. The first thing we do to reveal the structure of our Hessian is rotating it into a convenient frame using the singular value decompositions of F and D. H hat has a fairly tractable block matrix representation over here, which now only requires us to solve 2x2 eigenproblems. All of these intermediate variables, alpha 1, beta 2, and tau, represent derivatives of psi with respect to the invariants, and also singular values of D, which you can check the paper for to see more details on. Plugging in our specific ARAP energy, we note that the eigenvectors are understandable as 2x2 matrices. Two of the four eigenvectors have off-diagonal non-zero entries, which represent rotation modes, and their corresponding eigenvalues are here. The other two eigenvectors are the scaling modes in two directions, and we can see that in our rotated frame, the eigenvectors are pretty clean and have clear physical meanings. Putting all of the modes together, we have 6 total eigenvectors for ARAP, and we note that this whole method is generalizable to all I1 and I2 dependent deformation energies. The analysis for volume-preserving energies is slightly different to all of this, and we refer the reader to the paper to see more details on what exactly to do with those. With these eigenanalyses in hand, we have several applications. We'll showcase 2 of them here. First, we will show how to apply our analysis to construct spectral preconditioners for projected conjugate gradient solvers, along with a slightly more unified projected Newton method for physical simulation. For the first application, we want to assemble a preconditioner that improves the convergence of PCG that solves the linear system at each Newton step. Spectral preconditioners are used as preconditioners for linear systems AX equals B, and you start off with a preconditioner matrix B. Specifically, the spectral portion comes in at the application of a low-rank update on some base preconditioner B0, which can be anything, including basic block-Jacobi preconditioning. Most of the time, this preconditioner matrix is essentially just the block-Jacobi matrix, with this low-rank subspace update generated by this matrix Z, which is a basis consisting of low eigenvalue global eigenvectors. However, getting this matrix Z is a little bit tricky, since our global system matrix A, or in this case the global Hessian, is of very high dimension. We'll recall that our global system matrix, the Hessian of the deformation energy, is actually a sum and split of several local Hessians, of which we do have analytic eigensystems. But when you actually perform the scattering using so-called scattering matrices J sub I, you can perform a little bit of global eigenvector approximation simply by constructing linear combinations of these local eigenvectors. For example, here, using weights omega, we simply just sum up these local eigenvectors. Now, obviously, you can't just sum up eigenvectors in order to get eigenvectors for sums of matrices, but since this is a preconditioner, we are allowed to approximate a little bit over here. Since the weights can also be fitted from exactly numerically computed global eigenvectors, once at the start of the first Newton step, later steps we choose to simply reuse these omega values and assemble Z from the local eigenvectors using this equation, which is just a matrix multiplication, essentially. So, now we have a way of efficiently estimating Z to assemble the spectral preconditioner. To test performance, we apply our preconditioner to solve for a surface parameterization problem, that is, to minimize ARAP energies of texture coordinates. Here are some results from 3 examples where the checkerboard texture's task essentially is to distribute itself uniformly over the surface of these objects. This is a video showing how the parameterization evolves under our optimization and how they converge through, small amounts of Newton steps. as a comparison, the minimization of ARAP energy can also be solved through popular local global solvers. But compared with directly doing a global high-dimensional Newton solve that we use, the local global solvers fail to converge a little bit. Now, this does seem a little bit weird, but once we actually investigate the wireframe of this mesh, we see that the essential difference here is that our method is slightly better at handling ill-conditioned meshes that have intrinsic inversions and other things in them. So that's a plus on our end for a slightly more robust algorithm here. In terms of timing, here we show a breakdown of our method, numerically solving the exact global eigenvectors with low eigenvalues. Has a little bit of overhead, but we only need to do it once for the first Newton step. In later Newton steps, the global eigenvectors are constructed from the analytical local ones, which only takes a small portion of the runtime. And here we also plot the number of projected conjugate gradient iterations it takes to converge at each Newton step. Our method takes significantly fewer iterations compared to the base Bloch-Jacobi preconditioner, and we also compare with more modern preconditioners such as the algebraic multigrid method. The algebraic multigrid method has similar iteration counts compared to ours. And if we look at total runtime, of course, our speedups are also pretty good compared to both. In the case of Bloch-Jacobi, our speedups are in the range of 2x to 3x. And similarly, for the AMGCL, we have slightly more speedup since the overhead of actually applying the multigrid preconditioner takes a little bit more time than our matrix multiplication, essentially. Our second application is for a slight improvement on unified projected Newton methods. Or essentially, we're showing how Newton solves can be sped up using our position-based eigenanalysis. Looking back at our system matrix, the energy Hessian is not actually the only term computing or contributing to the large system matrix when doing dynamic simulation. We also have the mass and dampening term here, and since the mass matrix is positive and diagonal, it can offset some negative eigenvalues from our Hessian H. This makes it unnecessary to filter all of the negative eigenvalues. And our position-based eigensystems can also directly correspond to entries in the mass and damping matrix. This allows us to come up with a more conservative filtering strategy by jointly looking at all three terms in the system matrix. Now, we only filter eigenvalues that are lower than a negative threshold per element. This way, our projected system matrix can be closer to the original matrix while still guaranteeing positive semi-definiteness, which means that the system matrix can be more consistent across each Newton step, and the descending direction of Newton's method is better guaranteed, along with generally faster Newton convergence. We test our new projection strategy on 2D simulations, including two scenes with both the ARAP and the stable neo-Hookean energy. So this is a 2D porcupine ball falling down here. And also a block of cheese falling down a few cubes here. Additionally, we do the same thing with the stable neo-Hookean energy for both of these cases. Now, taking our porcupine ball with the stable neo-Hookean example, we do a little bit of analysis on performance. Specifically, we count the number of eigenvalues that are filtered using our method compared to using normal F-based eigendecomposition. You can see that very few eigenvectors actually need to be clamped if we use our superior strategy, which unifies all three terms of the system matrix. We also compare the number of Newton steps required for convergence at each simulation time step for this porcupine ball simulation. You'll notice that the two types of F-based filtering, where we clamp negative eigenvalues to 0 or take the absolute value, both converge slightly slower than ours. More concretely, our method clamps eigenvalues at a factor of 30 times lower, essentially for both of these scenarios, 30 to 20 times lower. And also we achieve a 2 to 3 times speed up in simulating the entire simulation. That's all about the theory and application of our work. In terms of future work, a direct follow-up would be to extend these spatial eigenanalyses to 3D simulations. And for preconditioners, we can also try different combinations of base preconditioners to have even better performance. Thank you for your time.